So, welcome back, and we're here again with a new set of exercises. And this time it's going to be about subspaces. Subspaces and linear independence and generation, and also basis of subspaces. So, let's start. The first exercise asks to look at these sets of vectors in R3 and to tell whether they are independent, they generate, and or they are a basis. So let's just do it. So as for S1, you see can't be generating. Why? Because it has just two vectors. So in order to be generating in R3, you need at least three vectors. And what about independence? It is not independent, because it contains the zero vector. When you put the zero vector in any set of vectors, then you break linear independence. It's very easy to see. So that was it. And what about the second? You can see, by inspection here, you can see that the third one is actually the first one plus 2 times the second one. So, I mean, this tells that they are not independent. I mean, what's the point in being independent? If you recall sorry, the definition, being independent means actually that your vectors do not have non-trivial relations. I mean, and this is a non-trivial relation between them. If you rearrange things, you can write, for example, 1, 0, 0 plus 2, 0, 0, 1 minus 1, 0, 2 equal to 0. And this precisely tells, this is precisely a relation between these vectors. So they're not independent, and can they be generating? Well, not really. Not really. There is an observation one can make here, and it's actually we'll actually come back to it in the last exercise and make it more rigorous. But you can observe, if you consider this matrix, then you know that you know that being independent means that this is 0, and being generators mean that this is 3. So, I mean, if you have, this is something you can use. If you have 3 vectors in R3, then they are independent if and only if they generate. This is a useful observation. So they're not independent, they can't be generating. Okay, what about the third? Well, here, if you look at this here, you see that the first 3 vectors are actually the canonical basis vector in R3. Should recall this. And another thing to say is that if you have more than 3 vectors in R3, then they can't be independent. for dimension reasons, if you want. And so these are not independent, for sure. Are they generating? Yes. Because these do generate it. I mean, if you have a set of vectors and a smaller set of them is generating, then the set is clearly generating. So no problem. So okay, let's go for S4. S4, which is this 1 2 1 0 0 1. Okay. So what about this? Well, let's just see. Is it 0 1 1? Sorry. Fine. So let's first look. They can't be generating. They don't generate. Because they are just two vectors in R3. They can't be generating. Okay. What about linear independence? Well, one can check it directly. You can solve the system. Well, you can solve the system and look if you have just one solution. Well, let's just solve it directly. You can use Gauss elimination if you want, but it's no, this is just this. Okay. So this gives you this, and this gives you. So yeah, you have x equal to 0, so then you can get y equal to 0. So okay, they are independent, but they don't generate. And what about the last one? So S5, which is 1 3 2 0 2 5 0 0 7. Okay, let's recall that as we observed before, a set of vectors in R3, if there are 3 vectors in R3, they are generating if and only if they are independent. So we can look at this matrix. But it's like, you can try to solve this system. Again, it's very easy. So you do x equal to 0, 3x plus y equal to 0, but then here you find y is equal to 0, and then here, and then you find again, so this. So okay, they are independent. They are independent, and as we said, they are independent. There are 3 vectors in R3. They are independent, so they generate. And this means that, by definition, this means that they are a basis. Okay, fine. Fine, very good. Okay, that was the first one. Fortunately, it was quite quick. What about the second one? So determine a basis of the kernel and the dimension of the image. So a basis of the kernel and the dimension of the image of the following matrices. So here, the point is, we just have to solve some linear systems. So the kernel, just to remember, the kernel of A, in general, are vectors such that they are sent in 0. Okay, so we just have to solve for A. We just have to solve this system and see what happens. So this gives, you can use Gauss elimination, but I mean, they are very easy, so you can also do them directly. So here you see that this equation here is actually 2 times that this equation here. So it's redundant. you can just forget it. So the only thing that matters is this one. And so you can put, for example, I don't know, x to be, or y to be a parameter t, and then you find out that x is equal minus 2t, and so the general solution is going to be this. So this is going to be t minus 2, 1. And so you see that a basis of the kernel is given by this vector. And you can check that it actually works. And what about the dimension of the image? Then recall that you have the famous formula. So the dimension here is 1. So the dimension of the image has to be 1. That's it. And what about the second one? Same thing. Only it's a rectangular matrix, not a square matrix. True. Okay. Very good. So let's again solve this. Perhaps here it's best to use the Gauss elimination, so let's just not write the zeros back then. This is not, has to be this. Okay, let's just reduce this matrix into row echelon form, or at least in a nicer. So let me multiply, I don't know, this second row by 3, so 3, 6, minus 3. Okay. So, and then we can add. So this 0, 7, 0. Okay, very good. Well, actually almost there. So you can, like, this is it. Now you can try and solve the system. So it's going to be minus 3x plus y plus 3 this, and this is going to be y equal to 0. So it's going to be okay, so it's going to be 3x equal to 3 this, which then means that x is equal to z and y is equal to 0. So you can put z to be a parameter. Let me just I don't want to make another. Let me just shrink this a little bit. Okay. Can I shrink? Yes, I can. Okay. Very good. So okay, then let's put let's put z equal to t. Then what you have is that x, y, z is, I don't know, t, 0, t, so it's t, 1, 0, 1. Very good, and this is a basis of the kernel. This vector makes a basis, gives a basis of the kernel. So again, here, be careful. So the dimension formula tells that 3, which is the number of columns, so you always think of a matrix as something like here, this input, and this is the output. So the input is 3. So you have to do this. This is again the dimension of the kernel plus the dimension of the image. and so this is 1, and this has to be true. So this is I realize now that I didn't review the notions of kernel, image, and linear independence and generation. But I mean, this is probably had to, but well, let's say that these are exercises, and we take them for granted, and but yes, and at a practical level, just as a recap here, if you have in general, let's say that in general, just to give a practical way of understanding this concept in general, if you have vectors, I don't know, v1, vk in some Rn, you can construct the matrix A. The columns is given by the vectors, so columns, okay, and you know that this is independent if the kernel of A is 0, and this is generating if the image of A is all Rn. So you have to look at practically you have to look at this matrix. This is a way of understanding things, and I mean, this is just the definition of linear independence, and this is also the saying that this is also saying that the span, just by definition. So recall that the span is just given by the combinations, things of this form. Okay, that was just just to recap. Should have said this before, but yeah, sorry. So let's go on. That was kind of easy, yeah. Okay, so now finally we have subspaces. We have some subsets of R2, and we are asked to tell which of those are subspaces and which of those are not. So what makes a subspace? If you have to have the zero vector and it has to be closed with respect to the sum, if and multiplication of scalars. Okay, so this is the definition, and we have to check this. Just recall, kernels, images are always subspaces. The span is a typical example. The span of some vectors is an example of a subspace, very typical one. And as we've seen before, the image of a matrix, you can say that it's the span of the columns of the matrix, and the kernel of a matrix gives information on the linear independence of its columns. Okay, very good. So let's look at these things. Well, the point is, linear subspaces have to be made of essentially they're defined by linear stuff. So for example, linear equations. So whenever you have something which doesn't look like a linear equation, then you're quite sure that it won't be a subspace. But there is also something more. They have to contain the origin. So subspaces are like lines, things like this, or planes, I don't know, like this, but through the origin always. So you can have something which is like looks linear, but it's not a subspace. For example, a line like this, it's not a subspace because it doesn't cross the origin. So, but that said, let's look the first. Well, we expect it won't work, but how can you prove this? Well, subspaces have to be closed under multiplication of scalars. So you see that 1, 1 lives in this, let's say, this thing. But 2 times 1, 1, it's 2, 2. And it doesn't. Well, because, yeah, this is not of the form, if this is x, this is y, has to be x equal to y equal to x squared, but it's not, so it doesn't work. So what about the second? The second, if you draw it, is actually one of these lines, but they don't cross the origin. You can see it immediately. So the origin doesn't live in this. Why? Well, because it's very immediate. Well, so it's not a subspace. And what about the third? We rewrite as so t, x has to be t in 3t, so which is then t 1 3, and t is in the real numbers. So this is by definition the span of 1 3. So it's a subspace. And what about a basis? Well, basis, this is a basis. It's clear. It generates by definition, and it's independent, it's just one vector. Very good. One vector and it's not 0. So what about the fourth? Well, let's say that it's of this form, yes, and then you can rewrite it at t squared 1 3 14r, and there's a problem here. For example, looks okay-ish, but what if, 1 3 lives in this thing, but -1 times 1 3, which is -1 minus 3, doesn't, because, well, it's not of the form a square number times 1 3. The point is that t square is always positive. So you see, this is positive, so this can't be here. And yeah, so this is not a subspace. And let's look at the last one. Let me just shrink so I don't. Okay. Very good. Okay. So the last one is a little trickier. So it looks similar. So you can, if you want, rewrite it so 5 So this is again t. You can put this t cube here, 1, 5. And yeah, here what is the point? I mean, the cube function does not have the problem of the square function. So indeed, the thing is that here, this t, when t spans all real numbers, if t runs through all real numbers, then the same is true for t cube. So we have a claim here, actually. Let me go here. Well, the claim is that actually this strange thing is the same as a set the regular span we know and love. So how can you prove this? It's an equality of sets you want to prove. So we have to check that first you have an inclusion like this. So you have to fix an element in here, let's say of the form this, and we want to make it an element of this form for some t in R. Is it an element of this form? Perhaps this is a little bit confusing. Let me just use another variable here, s and s. Well, if you take s to be t cubed, then and lives in well, we've run out of names. Let me just not call this s, but I don't know, s, I don't know, u, which lives in this, is definitely of this form. The other one is going to be the more difficult. Take an element of the form S1, 5, and we want to find, I don't know, we want it to be of the form cube of something times 1, 5 t, such that t cube 1, 5 is equal to s1, 5. Well, but you can do this. We can take t equal to the the cubic root of s, which always exists. It always exists. So at the end, since we checked this equality, conclude that this last thing is actually the span of 1, 5, and this is again, as before, this is a basis, and it's a subspace. That's good. We finished the exercise, and so there is just this last one, which is actually a theoretical exercise, but it's something we've already seen. So perhaps let me take this as the moment when we actually start already writing the detailed solutions, and use this exercise as an excuse to like review that result on generating generating linearly independent vectors. So let's write a proof. Let's try and write it directly. Well, let's say we're confident enough. So what can we do? Let's be very detailed and very verbose. We recall that this is something we've already said, but let's just repeat it. Let's write this. We consider the matrix A whose columns are the given vectors. Okay, we recall that well, k is equal to n here. N is linearly independent if the kernel of A is equal to 0. And it is generating if the image of A, which is, by the way, the span, by definition, the span is equal to ORN. We recall the formula. So we have that n is equal to the dimension of the kernel of A plus the dimension of the image of A. So now we have to prove an if and only if, so we have to first prove one direction and then the other. So if these vectors are independent, then the kernel is trivial and the dimension of the kernel is equal to 0. Hence, the dimension of the image is going to be equal to n. Okay. Okay. Which means that means that actually the image has to coincide with Rn. I mean, this can be perhaps a little bit tricky to accept, but it works. If you want, if this is not all Rn, well, it doesn't work. I mean, it's like this. What I'm saying is that one should perhaps I confess that, well, you see, when you write something, then things come up then that you don't really always expect. But I mean, this is true. This claim, this claim we should like prove better, not just state it, but we should perhaps check it more rigorously. But it's true. It's definitely true. So let's just accept this and pretend that this is something we know, which we can actually pretend. Let's go on. Which means that image is equal to Rn, hence this is by definition, generating. Very good. So, on the other hand, if these are generating, then by definition well, let's remove by definition here. It's not really that nice. Okay. Then by definition, yes, by definition, this means that image of A is equal to Rn. Okay. Okay, fine. Hence, from this, we deduce that the dimension of the kernel of A is equal to 0. This implies, and this is also something that one should check, but let's pretend we know this, that kernel of A is just this. So this is by definition the linear independence. Okay, so this is okay. A few comments here. This is interesting because, well, I've tried myself to write down a detailed proof without first trying and like just at my first attempt. And you've seen that at some point I hesitated, and I realized that some points were not as clear as I was thinking they were before. So you see, I mean, this is interesting if you want, because it shows you that it's really important to be careful and to do this work of like trying to write every detail, because as you do this, you find out that perhaps something which you first overlooked, then it's trickier than you thought than you thought it was, and you are forced to look deeper into it. Now, in this case, we are not going to like investigate more this claim. So if the dimension of the image is n, then this coincides. This should perhaps be checked. It's not very difficult, but should be checked. Should be definitely checked. And and also this thing, which is probably easier. If the dimension of the kernel is 0, then the kernel is the trivial subspace. So these two things should have been probably checked, better checked. We don't do this here, but in principle, one should, if one wants to write a book, which is not our case. I mean, let's just be clear about this. And I mean, this argument would be perfectly acceptable as a solution, given that you know the theory. And actually, I mean, this exercise is kind of special because it's something one can actually, that actually is not, can actually, something that doesn't need to be really proved, because I mean, it's actually part of the theory. This is more of a like theoretical exercise, but you can, I mean, in general, you'll be able, you'll be allowed to accept this result and use it in the applications. But in this case, well, the point was at least try and give a proof, and this is okay, save for the fact that if one wanted it to be, to be really 100% detailed, one should have been more careful about these claims, this and this. So, okay, but no worries. I mean, this is not going to be something one normally finds in an exam, so no problem. Let's just go back and write now detailed solutions of the original exercises. So, and this is going to be easier. So let's go here. Okay. Exercise 1. Okay. So S1, let's see, let's write this. What is this? It's not independent and not generating. Is not. And not. Well, let's be careful. It's not independent because it contains the 0 vector. This is perfectly acceptable. It is not generating because it has true less than 3 elements. Okay. And you know from the theory that any set of vectors to be in R3 to be generating, it has to have at least 3 vectors. So, let's see. The second. Okay. That's true, is not independent. Because, and then you can just write the relation. If you want, write the relation as follows. 1, 0, 0 plus 2 times 0, 0, 1. Okay. 0, 0, 1 minus 1, 0, 2 is equal to 0. And I mean, this is a non-trivial relation. But this is it. It is not generating. If it were, it would be let's say it has so if it were generating, it would also independent. Okay. Okay. Very good. The third. This is not. Well, 2 times 5, 7, okay. Okay. But it is generating. Because it contains which is canonical. Okay. Very good. So as we said, if a set of vectors contains a smaller subset which is already generating, then of course it's generating. So the fourth and let's say this is not generating because it has 2 less than 3 vectors. It is independent because, and here you can say this because the kernel of the matrix 1, 2, 1, 0, 1, 1 indeed the linear system yields from which we conclude that okay, very good. The fifth, just let's write this before S5 is independent. Then it will be generating, and vice versa. Since it has precisely 3 vectors, it is indeed independent, because, and then you can just 1 to 3, 0 to 5, okay. Gives sorry. From which x, this is immediate. Okay, so this is it. This is it. Okay, fine. For the first one. What about the second one? Okay. So, we solve. First, we solve the system, which is 1 true is equal to 0, 0. So, which is equivalent to just this equation. We find minus 2t, hence we conclude that the kernel of A is equal to vectors of the form minus 2t t, which is equal to t minus 2 1 for, okay, which is the span minus 2 1. We conclude that is a basis from the formula so this is true dimension image is equal to 1. Okay. Is this correct? Yes. Yes, minus true 1. Very good. The second seems very similar. We solve the system, and this is okay. One true minus 1. We use Gauss elimination B. So here let me be a little bit streamlined. 1 true, so this take 1 and the second, so 3 times the second plus 1 as replacement. So zero, 7, 0. We can reduce. No, let's see. First, and so minus 3, 1, 3, 0, 1, 0. Hence, we solve equivalent so minus 3x plus y plus 3 this and y to 0. Very good. So which means minus 3. Well, let's say that x equal to this and y equal to 0. So let's see what were our choices. Okay, we set and we conclude that the kernel of B is given by things of vectors of the form T 0 T, which is T 1 0 1, and this is exactly the span of this. Okay, is it correct? Okay. So 1 0 1 is a basis of kernel B, and the formula, so be careful here, the input is 3 columns, has to be equal to the dimension of the kernel A plus the dimension, this is not A, it's B, sorry, the image of B implies, if you want to put this is again 1, implies that the dimension of the image of B is equal to 2. Fine, we made it. Sorry, we made it with the second exercise. So only one left, only one to go. Okay, yeah, let's do this here. Oh, sorry, here. Fine. Fine. Okay, so let's try and be not so long. Let's make it quick here. So exercise. So 1. This is not a subspace. Space because 1, 1 leaves well, see here, there is a problem. These sets have no names. They have just numbers here. So let me just put some notation here. So let me call this V1, this V2, this V3, this V4, and this V5. So the solution will be more streamlined, and it's something you can always do. So you can always give names in order to streamline the presentation, your argument, because this lives in V1, but 2 times 1, 1 does not. 2 is different from 2 squared. Okay, so that's okay. The second, okay, the second was the fine line. This is not subspace because 0, 0 does not live there. I mean, you can check it. Y has to be x plus 5, but 0 is different from 0 plus 5. Okay. 3. What is this? This is a subspace. Indeed, V3 is equal to T. Is it correct? Yes. Which is exactly the span 1, 3. Basis is given by this. Okay. Fourth was the one with the t squared. This is not subspace. Indeed. What was it? So lives in this V4, but -1 1, 3 doesn't any element. What is this T? Before is such that both components are greater or equal than 0. Okay. So this is the difficult one. This is a subspace. Indeed. We can prove that V5 is going to be equal to, let's just rewrite it, which is 5, was it 1, 5? Yes. Is actually equal to S 1, 5, S in R, which is then again span 1, 5. And yeah, so let's check this. How can I write it nicely? Sorry. So V5 is equal to this. Let's say it's actually here. Okay. Indeed. Call, I don't know, W5, this span. If V is in V5, then it is of the form T cube 1, 5, taking S equal to T cube, we immediately see that V is also in W5. On the other hand, if this any vector lies in W5 in this span, then it is of the form S15 setting T equal to the cubic square root of S, we deduce that V, which is equal to this, is also equal to this T cube. So it lies in V5. We've just proved that V5 was contained in this W5 and W5 was contained in V5. Hence, y is equal to v5 as claimed. And well, this vector is a basis of v5. This is it. This is it. It was not that easy, this last one, but this is a nicely written solution. Well, perhaps this 3 here is a little bit not nice. This is better. Okay. Very good. We managed to do everything. And okay. So, see, as usually, we've written nicely detailed solutions. Few remarks. Well, I don't know. Here we wanted to prove an equality of sets. In order to prove an equality of sets, what you always do is check that one set is contained into another and the other is contained into the first one. This is always what you do. And yeah, to check that some set is contained into some other, then you fix an element here, for example, and you argue and try to check that it lies in here, in the other one. Okay, but yeah, apart of this, the exercises themselves were pretty standard. Well, perhaps yes. The only interesting part was, as remarked before, this 4th exercises where while I was writing the proof, I realized that some parts were not so clear as they should have been. So for this exercise, which is like kind of special, so we don't worry about this, and we still accept this proof by like assuming that the tricky parts we've already done before. But yeah, in general, this is. I mean, yeah, we can make we can say something here. Well, I mean, while writing a solution to an exercise, of course you have to invoke results from the theory. And I mean, in this case, there are many results you can invoke. I mean, everything you know from the theory, you don't have to prove it. You can like just you can just refer to it. It's fine, but you have to make it clear. I mean, the point in writing a solution is, well, convince someone. This is the point. And if you think that you've given enough details, have you made enough references, and that something doesn't need to be really checked because you think that it's very easy consequence of something of a theoretical result, or I don't know, then it's up to you. You choose the details you want to give. As for beginners, I always advise, choose wisely, and if you're not sure, then just give more details. Just be very detailed. Don't worry to spend more words than less. But it's important to underline and remark that the goal is always and will always be to write something which is clear, nice to read, and convinces the reader that you're doing right. And so you can really make him believe that your solution is actually something which is correct and it's good. This is your goal, and this is what you want to do when you write a solution. Okay, so that's all for today, and next week we'll have something more. again on subspaces and orthogonality that time. Okay, so thank you for watching and see you the next